All right, welcome back. This is video lesson 2 from Math 1910, and today we're going to be talking about definite integrals. So let's get started. There's a lot to talk about here. The main problem that we're going to be approaching is computing area under the curve of some function, under the graph of some function. So first, before we compute the area exactly, we have to know how to approximate it. So we have a continuous function f, and it's defined on some interval a, b. So this is going to be like, in general, we'll do examples where f is a specific function and a and b are specific numbers. But so how do we compute the area under the graph of f? So here's an example. So our function is y equals x squared, and we're looking at the interval from 0 to 8. So here's like, this is 8, right? And so this is the point 8 comma 64. And okay, so this graph is a little bit stretched horizontally to fit on the page, but I don't know, it's not really important to scale. Okay, so let's go through it. We're not gonna compute the area exactly at first, but we're going to approximate it. And here's how we do that. The first thing I'm gonna do is let's just draw a dotted line here. So this is 8. I'm gonna break the interval that I'm trying to compute the area over, 0 to 8. Here's 0, here's 8. I'm gonna break it into pieces. For this example, let's break it into 4 pieces of equal size. So this is 2, 4, and 6. Okay, and then I'm going to draw rectangles whose bases are the bottoms of, or the bottom of the rectangles will be like each of these subintervals. Okay, so the height of the rectangle will be given by the function at the right side of the interval. So looking at the interval between 4 and 6, here's the bottom of the rectangle, and the height is given by the value of the function at 6, the right side of the interval. So here's the rectangle. Okay, and I do the same thing for the other 3 subintervals. All right, and there we go. So I've drawn 4 rectangles. And you can see that like if I'm trying to compute the area under this curve, the rectangles are close, right? There's each rectangle, for instance, this area is actually underneath the curve. That's the area that we want to find, but then it's got this area here, which is kind of an error, right? That's area that's inside the rectangle that we don't want to include in our calculation. But okay, so that's why this is going to be an approximation. So to find the value that we're approximating, or rather to find the approximating value, we're going to add the areas of these rectangles. So with the area of this rectangle, well, we know how to compute areas of rectangles. It's just the length of the base, the bottom part, times the height. So the base of all these rectangles has length 2. And the height is given by the value of the function at the right side. So the value of the function at the right side here is 2. The right side is at x equals 2, and then the value of the function there is 2 squared, which is 4. But I'll just write 2 squared. Okay, so that's going to be the area of this leftmost rectangle. Okay, this one, the base is 2, and the height on the right-hand side is 4 squared. And we can do that the same thing. The base is always 2, and then it's the value of the function at the right side. And then this one is 2 times 8 squared. Okay, so I could be writing 64, but it's 36 for 6 squared and stuff, but I want to just keep it like this to illustrate the patterns. So we can write down the approximated area. It's approximately the sums of all these rectangles. So 2 times 2 squared plus 2 times 4 squared plus 2 times 6 squared plus 2 times 8 squared. Okay, so there's an approximation, and if we're clever, we notice that there's a pattern, and we can write this using summation notation. So we could write it as the sum. J goes from, let's say, 1 to 4. It's 2 times 2j squared. Okay, if you don't understand, if this kind of came out of the blue, this summation thing, you should take a minute and understand why this summation is the same as this sum of 4 things that I wrote here. Okay, so this is some number. Again, if we had a calculator, we could compute it. But for now, that's the basic idea of how we approximate. Here's the more general list of steps that we take. This is called the right endpoint approximation. You'll see why. The first thing we did was we chose a number of subintervals, right? I chose 4, but you could choose any number. And we divide the interval that we're dealing with into that many pieces, and it's important that they have equal length. So, well, it simplifies our calculations a lot when they have equal size. Next, we drew rectangles based on each subinterval, and the height of each rectangle is given by the function on the right side of the subinterval. That's why we call this the right endpoint approximation. And then we had a bunch of rectangles, and we can compute their area, which is pretty easy, and we get this thing we call Rn. That's the right endpoint approximation to the area under this curve over the interval AB. Okay, so let's do that one more time, but in a little bit more generality. So here's another curve. This is y equals f of x, and let's say this interval here is from A to B. Okay, so remember the first thing I do is I choose a number of subintervals, n. So here we're going to try to keep it as general as possible. So n is just some number, and we're going to divide the interval into n equal subintervals. Okay, so here's the first few subintervals, and here's the last one. Okay, so then we will draw rectangles over each subinterval where the height of the rectangle is given by the value of the function on the right-hand side. So we go up from the right hand to the function and draw rectangles like this. So this function's kind of flat here, so all these rectangles have about the same height. Okay, you get the idea. And then the last rectangle looks like this. Great. Okay, so I draw, and there are rectangles in here that I'm not drawing because I'm trying to think of the number as arbitrary, even though, I don't know, it's approximately 7 in this picture. So what is the height of each rectangle? So let's think about maybe, okay, it'll help us to give names to the points of this, the points in this subdivision. So let's call A x0, and then the next point will be x1, x2, x3, and so on. B is going to be called xn, right? We have n, capital N subintervals, and this is going to be xn minus 1. Okay. So how do we compute, say, the area of this rectangle? Well, the width of the subinterval, we took the interval, we took the interval from A to B and divided it into n equal pieces. So the width of that is going to be b minus a over n, right? B minus a is the length of the entire interval, and we're dividing it into n pieces. And the height of the second rectangle, which is the one that I have this arrow pointing at, the height is just the value of the function, which is f of x2, say. Okay? And so we have, and then the area is just b minus a over n times f of x2. All right, and to simplify things, we're going to call this b minus a over n. We're going to call that delta x. It's the interval width. So we get our area approximation to be this. Well, it's the area of the first rectangle. The first rectangle has base delta x, and the height of it is f of x1, right? That's the right endpoint of the first rectangle. And then we're going to keep adding rectangle areas, right? And we add all of them up. The last one is delta x times f of the rightmost endpoint of the last interval, which is xn. Okay? And again, we can write this as a summation. The sum as j goes from 1 to n of delta x times f of xj, right? Notice that the only thing that was changing in each of these terms is the index on x. So that's what we're looking for when we're trying to write things as summations. Okay, the last thing we want to point out before we go on is that we can actually write down xj in terms of a and b. So xj is, how do I get from a to xj? Well, I move over, right? If I want to get from a, starting here, to say x2, I move over delta x to get to x1, and then I move over delta x again to get to x2. So what that shows is that x2 is equal to a plus 2 times delta x. And in general, xj is equal to a plus j times delta x. Okay, so this is useful because we can actually use this to compute things, right? J is just an indexing variable, a is a number, delta x is a number. Okay, so that's that development. Let's summarize it. So that was called, this is the right endpoint approximation. This is exactly what we just wrote down. We call it Rn, and it's given by this formula where delta x is the interval width, b minus a over n, and xj is the right endpoint of the jth rectangle. Okay, so this formula, this is pretty important, you should memorize it, maybe, this one here. If you don't memorize it, you should at least try to remember like everything we did here, like how we came up with all of this stuff. All right, it's not that complicated when you really think about what we're trying to do, just approximate area by rectangles of equal width. But there's at the same time, there's kind of a lot going on. Okay, we could have done a left endpoint approximation where instead of picking the right endpoint of every subinterval, we pick the left endpoint. If we had done that, we'd get this, all right? So we get this left endpoint formula. It's similar, right? The only thing that's different actually is here and here, right? The indices of the sum, right? That's the only place it differs from the right one. Okay, so this is an optional exercise. Go back and do the exact same thing we did just a second ago using left endpoints, and observe that you get this sum with these different start and stop points. Okay, so now that we know how to approximate area under curves, we want to move towards computing exact area. So something we should notice about Rn and Ln, the right and left endpoint approximations, is they get more accurate as n increases. Okay, maybe you should pause and draw some pictures to convince yourself of this. But if I take more rectangles, right? In the previous case, I had 4, but if I had drawn 8 rectangles, then the error would have been smaller, and I get a better approximation of the area under the curve. Okay, and in fact, if I take n approaching infinity in the sense of a limit, then I actually get the exact area under the curve. So the area under the curve of, the function that we're trying to find the area of over the interval that we're given is the limit of either the right or left endpoint approximations as n goes to infinity. So what that means is, to calculate area exactly, we first find a expression for, say, Rn, and then take a limit as n goes to infinity. And sometimes you can compute that limit and you get the exact area. So we're going to do an exercise. We're going to calculate the exact area under y equals x squared over the interval from 0 to 8. Previously, we found the approximation r sub 4, but we're going to find r sub n as a general formula, and then take a limit as n goes to infinity. So if you want to try this exercise before seeing it, you should do that. You should pause the video now and see if you can try to do it yourself, and then watch the solution. Okay, so the first thing we're going to do is write down the formula for Rn. It's delta x times the sum. J goes from 0 to n, sorry, from 1 to n. Of f of, we called it xj, but then remember that was a times j delta x, sorry, a plus j delta x, where delta x is b minus a over n. B is 8 and a is 0, so this is just 8 over n. Okay, and n is, we're not saying what n is because we're going to take a limit as n goes to infinity later. So so f of x is x squared. So if I want to put specifics into this equation, I write delta x is 8 over n. I still have a sum as j goes from 1 to n. And then I'm looking at f of a is 0, and so I have j times 8 over n. Okay, f of this here is that thing squared, so I have 8 over n times the sum, j goes from 1 to n, of j squared times 64 over n squared. Okay, so now it's important, now we see why we want to review summation notation and summation calculating formulas before seeing this section, because we need to simplify this expression. To do that, the first thing we notice is that j is the indexing variable. This thing here is constant with respect to j. Even though it has an n in it that is, technically a variable in this context, we can pull it outside. So we take this entire thing and pull it, and put it over here. Meaning we multiply 8 by 64 to get 256, I think, over n cubed. And then we're left with the sum, j going from 1 to n, of just j squared. And then we look back and remember that formula said when we're calculating the sum of squares, we still have this 256 over n cubed. The formula was, let's see, it's n times 2n, sorry, n times, this is why you should just have it written down somewhere. It's n times n plus 1 times 2n plus 1 over 6. Okay, so we've removed all the summation stuff from this, and I'm going to rewrite it like this. I have 256 over 6 times n plus 1 times 2n plus 1 over n cubed. Okay, so the last thing is to calculate the area exactly. We're going to take a limit as n goes to infinity of Rn, and that is going to be, well, we're taking a limit of this expression here. The 256 over 6 is constant with respect to n, so we just want to find the limit as n goes to infinity of n times n plus 1 times 2n plus 1. Okay, so we could spend time trying to remember facts about limits, but I think we should focus on more important things. It turns out this limit is 2, okay? If you don't know why that is, you should go back and review limits, or if it's a real sticking point, you can ask me during office hours or something like that. Anyways, so this limit, this entire thing, is equal to 2, and so we have 256 times 2 over 6. So that's 256 divided by 3. Okay, and that's our final answer. So that's the exact area under y equals x squared over the interval 0 to 8. So now we're ready to start talking about definite integrals, which are very closely related to exactly what we've been doing earlier, which is computing area under curves. In fact, you can think of it as just notation for the area under a curve. So we write definite integrals with this notation, this squiggly s symbol. It's called the integral sign. This this dx here is, you should ignore that and pretty much think about it as just part of the notation for now. I mean, it'll become more important later on. But we read this as the integral of f of x from a to b, or the integral from a to b of f of x. Anyways, so it says here we're defining it as a limit of Riemann sums. I haven't talked about Riemann sums, and I won't. If you're curious about them, you can go look in the book. A Riemann sum is a more general version of the right endpoint or left endpoint approximations to area under a curve. Okay, so like I said, since this is essentially just notation for area under the curve, it isn't that surprising that when this limit of Riemann sums exists, we can actually compute the definite integral as either the limit of the right endpoint approximations or the limit of the left endpoint approximations. And we've actually already computed one of them. We computed the integral of x squared from 0 to 8. And remember, we got 256 over 3. Now, when I say that this is equal to the area under the curve, that's not exactly right. So the caveat here is that the definite integral is equal to the signed area under the graph of f. So here's a quick picture explaining what that means. So signed area means there are areas under this between the graph and the x-axis. So far all of our functions have been positive. Here's one that is not always positive, right? This is the x-axis. So I have some area on the top that is this is positive area, and then I have area on the bottom that's negative area. And the definite integral of this function is going to be the positive area minus the negative area, right? It's not the area, but it's not the sum of this area and this area. It's positive minus negative. So that's what we mean by signed area. That'll come up in the future. Sometimes you'll be asked to compute the unsigned area, in which case you'll have to do some trickery to make sure you don't accidentally compute negative area. But we'll see these in exercises that we do later on, and you'll eventually get a better understanding for it just by practice. Okay, so the last thing that we want to talk about is some properties of the definite integral. It's just one big list. Here it is. So this is a lot of stuff, but a lot of it might look familiar if you've been thinking about summation notation. So for instance, this and this are almost directly analogous to the linearity properties that we had when we were talking about summations. And this one here is also similar to something about summations, if you want to think about that. Okay, so to help develop your understanding of these integrals and how they're interpreted in terms of signed area, I suggest the following. You should try to justify all of these equations. And don't do that via the definition of the definite integral, which I haven't even told you. You should think of the definite integral as signed area and try to draw a picture to understand why each of these statements is true. So here's, I guess we can do this one as an example. All right, the left-hand side of this equation is the integral from a to b of 1. So if a is here and b is here, I'm looking at the area under the curve y equals 1. All right, so it would be this area. It's all positive, so I don't have to worry about the signed part. It's just the area right? And the area of this space is, well, it's a rectangle, and the width of the rectangle is the b minus a on the bottom, and the height is 1. So the area is exactly b minus a. All right, so that's what I'm talking about when I say like interpret these in terms of signed area. All right, so it takes some time to do these. I'm not going to go over all of them, but if you have any questions about any of them, you can ask me in class. And yeah, so we'll see a lot of definite integrals throughout the entire course. It's actually, the integral is pretty much the main point, one of the main topics in 1910 that we're going to be talking about. So that's the end of this lesson. If you have any questions, again, just talk to me during class or in office hours. Until next time.